Funding for this program was provided by the Annenberg CPB project.
Today, our hero for the day is André-Marie Ampère. Ampère was educated under the influence of the philosopher Rousseau, which meant that he was never really taught anything at all. He was simply placed in a well-stocked library and told, "Here, go learn." Well, in his case, that seems to have worked pretty well. He's known to have taught himself Latin and to have read Euclid and Euler and Bernoulli and various other mathematicians. In the meantime, however, when he was 14 years old, in the year 1789, the French Revolution descended. Ampère's father was a judge in the city of Lyon. And in the course of his normal duties, he had occasion to sentence a Jacobin to death on the guillotine. When the Jacobins took over the city some years later, Ampère's father, in his turn, was sentenced to die on the guillotine. Throughout his life, Ampère suffered the consequences of a conflict which is very common in Mediterranean societies, a conflict between a skeptical, doubting father and a deeply religious Catholic mother. This caused him, throughout his life, to work out grand metaphysical schemes that never amounted to very much. His personal life was extremely difficult, somewhat like Kepler's, you might remember. Not only did his father die on the guillotine, but his first wife, whom he married in 1799, died just 4 years later. His second wife turned out to be extremely nasty, and he wound up divorcing her. He had a son who was a useless wastrel. He had a daughter upon whom he doted, and she turned out to marry a crazy army officer. And throughout his entire life, he was always short of funds. But his professional life was even stranger. Starting in 1800, for 15 years, Ampère was a mathematician. Not a very good one, just barely competent. In 1815, he wisely changed his profession and became a chemist. And he turned out almost to be a great chemist. He almost discovered the element chlorine. He almost discovered the element iodine. He almost discovered Avogadro's law. As a matter of fact, what the rest of the world calls Avogadro's law, in France is called the law of Ampère and Avogadro. But in any case, in the year 1820, Ampère was 45 years old, and he was a thoroughly undistinguished minor figure in the world of science. However, he differed in one crucial way from every other scientist in France. He believed it was possible for important scientific discoveries to be made outside of France. In the year 1820, Ørsted's great discovery struck Europe like a bolt out of the blue. The other French academicians refused to believe it because it was impossible that anything so important could have been discovered in Copenhagen. But Ampère embraced the discovery immediately started to work out its consequences, and thereby made all of his great discoveries. And that brings us to our topic for today.
Okay, I need everybody in a 180 facing me and just point right over here. A 180 is not people behind me, okay? A 180 is a 180. I need everybody's attention. Everybody turn around and close it back in. Everybody remember how to pace count now. Another thing, don't bring back the box, okay? Some people want to bring back the box. They're on engineer stakes out there. All the boxes are there, okay? Nobody come back and say, well, Sergeant Fillmore, it's not there. Because I brought a class up here last week, and they were there.
At first glance, these U.S. Marines don't seem to have much in common with the 19th century French physicist, André-Marie Ampère. But as is often the case, there's more here than meets the eye. The challenge for Ampère was to explain a common but often baffling mystery of nature. The challenge for these Marines is to locate some well-hidden little boxes lying somewhere in these hills. And while those two challenges are separated by thousands of kilometers and about 150 years, the irony is that they both require the same thing: an application of the basic nature of magnetism.
The general purpose is 100 steps. Then I'm going to lift my head up and check my azimuth, looking under my index line. If my index line, right under my index line says 340, and I can still shoot my azimuth right towards Corporal Salazar, then I know that I'm locked on.
In 1820, Hans Christian Ørsted discovered that electric currents produce magnetic forces, and that those forces always make magnets point perpendicular to the direction of the current. This was a rich scientific discovery, but until Ampère could work out the consequences of Ørsted's experiment, it would remain little more than a single piece of a complex puzzle.
I'll do my right face, and I start marching until I get past the object. I'm counting the steps from where I made my last facing movement up to this point here.
So, like anyone starting out in a new field, Ampère advanced one step at a time, armed with Ørsted's discovery.
I took 3 steps this way. I'm going to do the complete opposite, take 3 steps this way. Once I get here, then I do another facing movement, and I'm off. Shoot my azimuth again, and there you go.
But these Americans have at least one advantage that Ampère lacked. Instead of working in these quiet, peacetime surroundings, Monsieur Ampère began his scientific career in the bloody pandemonium of the French Revolution. Ampère's father, Jean-Jacques, was a justice of the peace who was labeled an enemy of the revolution. As he approached the guillotine, Ampère Sr. scribbled a final note to his wife. I do not leave you rich or even in common comfort, but my greatest expense has been the purchase of books and mathematical instruments, which were indispensable to our son's education. But this expense was in itself a wise economy. Considering what his son mastered, the elder Ampère's money was well spent indeed. At the height of his academic career, Ampère was known as a natural philosopher, wise in the ways of science and how it could explain some of the more fascinating mysteries of the universe. Today, Ampère is best remembered for his work in electricity and magnetism. And that work started with the fact that electric current flowing through a long straight wire produces a magnetic field that circulates around the wire. But how does the strength of the field depend on the distance from the wire? If a tiny segment of electric current could exist, it would produce a magnetic field proportional to the inverse square of the distance. The direction of the field is related to the direction of the current by the right-hand rule, or the vector cross product. The field would be biggest when the current segment and distance vector are perpendicular. But electric currents can never exist in tiny segments. So any real magnetic field must be found by adding up or integrating the contributions due to each segment of a flowing current. The field, due to current flowing in a long, straight wire, is always perpendicular to the wire and decreases as the inverse first power of the distance from the wire. The net result is a field that goes in circles. The lines of force are circles concentric with the wire, and the field is the same all the way around each circle. On the other hand, if the wire is bent around into a loop, the current flowing through it produces what is known as a dipole field. A helical winding, or solenoid, is like a stack of current loops. It creates a field much like that of a bar magnet. If the solenoid is bent around into a circle, the donut it forms is called a toroid. The magnetic field of a toroid is contained completely inside the windings. There are no field lines outside at all.
Fire team leaders, hold up your maps so each member of your fire team can see what I'm talking about. Now, once I have it opened up the correct way, then I can go ahead and start shooting. Stick my right hand in my left hand. Elbows to my side so I know it's gonna...
Obviously, however, the Earth is no donut. Its field is like that of a bar magnet, with plenty of flux outside to apply force to the needle of a compass. For these Marines, the key to success is preparation and teamwork, which is why they've been getting down to basics. The basics of how to navigate with a compass.
You want me to write the grid square too? Was 5198?
Right under me,
Of
that's
course,
why it says
even among
340, and
experts.
I can still shoot. My azimuth right towards Corporal Salazar. Now.
And even with the help of a compass. Getting from one point to another can be quite a challenge.
Okay? Follow that grassy area all the way back to where it looks like it just drops off the edge of the earth. Okay?
But it's no less challenging than the task Ampere assigned himself in the early years of the last century. For example, he asked the question, if a current carrying wire exerts a force on a magnet, would it exert a force on another current carrying wire? To answer the question, consider the facts. A flowing current produces a magnetic field, and a magnetic field applies a force to a moving electric charge. Therefore, since an electric current is nothing but moving electric charges, it follows then that flowing electric currents apply magnetic forces to each other. Currents flowing in the same direction attract each other, and currents flowing in opposite directions repel each other. In fact, the unit of electric current is defined in terms of the force between two wires. Perhaps that's why it's called the Ampere, or amp for short. But Monsieur Ampère did something even more practical, and definitely more profound, than lending his name to a unit of electric current. Ampère created electrodynamics, the theory that magnetism is electricity in motion. It was a promising theory that, among other things, could explain the magnetic fields of straight wires, loops, or even a toroid. But what about the field of a bar magnet? Here, too, Ampère had the right idea, that there must be currents inside the magnet itself. He imagined that each atom of a magnetic material must have a circulating electric charge that produces a magnetic field. And in fact, the spinning Earth has circulating electric charges in its core, which create the magnetic field that attracts a compass needle. Therefore, the force that makes a compass always point north is the same as the force between two current-carrying wires. But putting that force to work often requires patience and accuracy. To make the measurement of angles as accurate as possible over long distances, one person sights along the compass and lines up another person at a distance.
About 52 degrees magnetic. Okay, now plot them out on here with the protractor.
These Marines are getting a first-hand lesson in the value of working together, a lesson that would seem to be just as valuable in the field of science.
Okay, I got it.
If so, it's a lesson that was not understood by Ampère. James Clerk Maxwell, or Michael Faraday. Although in their day, scientists tended to march to their own drummers, Ampère and the Englishman Faraday did work in parallel. For example, en route to their major successes in the field of electricity, both had been interested in chemistry and enormously influenced by the work of Sir Humphrey Davy. However, Faraday and Ampère were bound to go different ways. Where Faraday was intuitively brilliant, Ampère was simply brilliant when it came to dealing with numbers and symbols. And the law that bears his name is a mathematical description of the magnetic field as both similar to and different from the electric field. In an electric field, no work is done if a charge is moved around any closed path and back to its starting point. Therefore, when starting from any point on any path and returning to the same point, the change in electric potential is always zero. Therefore, the line integral of the electric field around any closed path is always zero. This is a fundamental property of electric fields. Magnetic fields are different. The current in a straight wire creates circles of constant magnetic field. And since the field is constant on each circle, the line integral on each one is easily calculated. It's equal to a constant times the current in the wire. The result is the same for any circle around the wire, and for that matter, for any path around the wire. The line integral of the magnetic field around any closed path is always equal to mu naught times the total current that threads through the path. This is called Ampere's law, and it's one of the fundamental equations of magnetism. And as such, it played a crucial role in the work of James Clerk Maxwell. When Maxwell sat down to forge a single coherent theory of electromagnetism, he started with Faraday's intuitive concept of lines of force, with Gauss's laws of electric and magnetic flux, and with Ampere's brilliant idea that all magnetism was electrical in origin. Of course, those insights had to be expressed mathematically.
The line integral of the magnetic field around any closed path equals mu naught times the electric current threading through the path. But for electric fields, the line integral around any path is always zero. The electric flux through any closed surface equals the net charge inside divided by epsilon naught. But the magnetic flux through any closed surface is always zero.
These are the fundamental equations of constant electric and magnetic fields.
Declination diagram. You don't have to worry about any of that. All you have to worry about is making sure that you have your azimuth on your bezel ring and make sure that your long limits line and your north-seeking arrow are lined up. That's it. With all this in mind, I'm telling you, as I told you before, there will be no flashlights out there. Okay? I know nobody here wants to fail. Does everybody understand the compass now? Everybody's going to be experts with this, right? Now's the time to ask questions. Remember, the only stupid question is the one that isn't asked.
Once Ampere realized that a loop of current would give a magnetic field in the same shape as the field of a bar magnet, a permanent magnet, he decided that maybe all magnetic fields would do to electric currents. That is to say, that every permanent magnet like this permanently had electric currents running around inside of it to generate the field. Well, that idea was immediately shot down in flames by a colleague named Fresnel. Fresnel pointed out that the materials that can be made into magnets, iron and steel, are notoriously poor electrical conductors, and that when an electric current runs through a poor conductor, it causes heating. And so he said, if Ampere's idea were right, then all magnets would always be warm, and they aren't, so it must be wrong. But he also gave Ampere a way out of that dilemma. He said, look, we know nothing at all about what goes on inside of atoms. Maybe the currents that cause magnetism actually occur inside of the atoms that make up the material. Well, Ampere embraced that idea and worked out a very clever construction. You have to understand that at the time it was believed that there existed something called the luminiferous ether. We'll hear much more about it later on, but it was in any case the medium that was supposed to carry light through space. And Ampere speculated that perhaps the ether was made up of enormous amounts of electric charge, both positive and negative, but ordinarily in perfect balance so that it was completely neutral, except perhaps inside of atoms. The idea he had was this. Here is an atom, like that, and here is some electric charge running through the ether. Positive charge running together with negative charge, like that, so that the two of them balanced and had no effect at all. But once they got inside of the atom, they could split up. The positive charge could run around one way like that and then come out again. The negative charge could run around the other way like that and then come out again. Now, the effect of the positive charge running around this way would be an electric current running around with the positive charge like that. The effect of the negative charge running around this way would be an electric current running in the opposite direction because it's negative, like that. So the net effect is of a complete loop of current, which would have a magnetic field looking just like this. And that meant that if the atoms of a piece of material all had these electric current loops in them, all running around in the same direction, the material would have just the properties of a permanent magnet. That is a very peculiar idea. There are parts of it that we still believe to this very day. We do believe that there are electric currents running around inside of atoms, and that those currents give rise to the magnetic properties of matter. But we no longer believe anything about the luminiferous ether being full of charge and all of this business of it splitting up inside of the atom and running out again. This picture is a splendid illustration of the very strange fact that it's possible in science to have an idea that's utterly brilliant and completely wrong. But it's part of that scaffolding that we're always building in order to make progress. In the course of time, opinions about the importance of events tends to change. Heroes in the history of science come and go. But one thing is certain, Ampere's name will always be current. All right, don't take any wooden magnets, and I'll see you next time.
Funding for this program was provided by the Annenberg CPB project.